Good day, ladies and gentlemen. This is the presentation, Thermoelectric Measurement of Nanoevents. Nanotechnology itself doesn't represent anything new. It was already there as atoms and molecules previously existed. The only difference is that today we can actually measure them. New technologies allowed those measurements and actual imaging of these nanoevents. Applications of nanotechnology yet are still limited due to us not knowing enough and not seeing exactly where we can use them optimally. And there's a very big gap between the current state of technology and the everyday use that we use them in. Integration of nanotechnology is into nanosystems, because into macro system it is applicable, and carbon nanotubes and carbon fibers and different materials are used for strength enhancement. Nanotechnology can't just be put into macro systems. It has to be integrated into microsystems. Now, it's interesting that nanotechnology enables us to a variety of applications. We can develop sensors who can detect minuscule amounts of chemical and biological reagents from the air or any other medium we would like to. They can be used for insulation of micromechanical systems. We can also create small nanocapsules that use localized drug delivery for cancer treatment. Yet all these ideas are pretty far away from actual everyday use. We actually are not able to control nanosystems by actually using, just like driving a car. So we don't have a steering wheel. The only thing we can do is, once we have nanoparticles deposited on a certain surface, or we have nanoparticles within a certain fluid, the only thing we can do is change the environment, change the pH of the water, change the acidity of the water, change the temperature of the water. Based on the changing of those environmental conditions, we can change the nanosystem and its functionality. Now, microscale systems, when they're fabricated, the basic technology that is living on and on and on is lithography. As simple as it is and complicated as it is, this technology developed all the computers and everything you see around you, and still is. Yet, lithography requires cleanroom access. There gotta be other ways to create microscale systems that are very cheap. One of the technologies available is called xerography. Xerography is a rapid prototyping system. It can be done in room conditions, so pretty much in your garage if you want to, and the only thing you need is a double-sided tape and 2 microscope glass slides that you can buy pretty much in any better supplied store. Now, this is actually, on the left side you can see actually a model, on the right side the actual fabricated chip. So we have 2 microscope glass slides, we have 2 ports, inlets and outlets, and we have interfacial layer. The interfacial layer is a double-sided sticking tape. It is cut on a cutter or a laser cutter, or the inlet and the outlet itself can be used stuck with super glue or any silicone adhesive you would like. They can also be used some more sophisticated technologies called plasma bonding, or it really does not matter as long as you get the ports to be tightly on the glass surface and not to be able to withstand a certain pressure that you'll be later on applying. Thermoelectric measurement principles are quite simple. We have thermopiles. Thermopiles basically are very complicated thermometers that you use to measure very small temperatures. Now, the precision of these thermometers is 0.3 micro degrees centigrade. Now, that is very, very small in comparison to a usual thermometer you use at home to measure your temperature. It measures within 1 degree. Now, to understand that a little bit of any kind of electrical noise, any electrical appliance around it will create noise, and any change, even the smallest change, will create a bad measurement, you have to thermally and electrically insulate that measurement. Now, for your question how sensitive the system is, if you enter my lab that is around 60 square meters, and if I have a working thermopile somewhere on the other part of the room, if you enter the room the same second, the thermopile will detect you. Now, will it be charge based because your charge is you have all your clothes and statical charge, or will it be temperature? It really does not matter. Immediately, the moment you enter, it will detect you. That is how sensitive it is. Now, a microchip system, if you look, is quite simple. So you have an inlet, an outlet, and you have two glass slides and the adhesive layer around that fluid that are containing it within the chip. And now you can distinguish a certain central part of the chip for a certain thing you want to do. That we would call a measurement zone. Now, in thermoelectric measurements, it's very interesting. You'll see small yellow rectangles on the bottom below these channels. So if you have one chip and you have a certain chemical and a certain concentration flowing through, you will get a certain voltage. If you have the same chemical in a higher concentration flowing through, because of all these chemicals interacting with each other and creating more heat, you'll increase the temperature and you'll increase the voltage output. So we will know, based on the temperature readings, that you have a higher concentration in flow number 2 in comparison to the flow number 1. Thermoelectric measurement can measure protein conformal change. What does that mean? Some chemicals, some biological reagents are very, very long chains of multiple biological reagents. Now, if you heat them up, they will actually coil together, or actually they will then split apart into threads. You can see 4 rectangles, big rectangles on this picture. 2 of them on the left, 2 of them on the right. The 2 left one have a certain temperature, each of them exactly the same temperature. They have a heater under them, and they have a thermopile measuring the reference measurement and measuring the actual part that has the sample and the voltage difference between them. If we, on the right side, see another 2 rectangles, and you'll notice that the protein changed in its form. It has the same amounts, the same yellow, blue, and red dots. It has the same blue wires between it, but it changed. Now this change is interesting. What we did is we heated up both the reference measurement and we heated up the sample. The difference that happens is part of the energy of the heat that we invested into the sample did not only go on the heating up of the water and of the protein, it also was spent into changing the conformation of the protein. That would be the end of the presentation about thermoelectric measurements of nano events.